10 tractors that could pull a tank. Not every tractor was built for farming. Some were engineered to move what no one thought a tractor ever could. Across decades and continents, a small number of machines emerged, not as experiments, but as solutions to an unsolvable problem of weight. In frozen military zones, thawing oil fields, and saturated farmland, they pulled loads that rival the mass of modern battle tanks. These machines weren't designed to impress from a distance. They were measured by what they could drag when every other option failed. What follows isn't a list of prototypes or museum curiosities. Each tractor you're about to see has proven, under real-world pressure, that horsepower alone doesn't define strength. Torque, traction geometry, frame stress. This is where machines either give out or break through, and in every case on this list, they pulled through. Sometimes literally, dragging more than 100,000 pounds across gradients and ground types that stall armored vehicles. These are the 10 tractors that proved, under real load, that some machines weren't built to compete. They were built to move the unmovable. Don't forget to press and hold that like button, leave a comment, and hit subscribe before we begin. Ranked 10th, JCB Fastrac Two, speed over strength. Not every machine enters the record books out of necessity. Some are built to challenge assumptions that were never meant to be questioned. The Fastrac Two wasn't created to till fields or haul grain. It was re-engineered from the ground up with a singular objective: to become the fastest tractor ever recorded. Developed by JCB, a British manufacturer more renowned for its construction equipment than high-speed machinery, the Fastrac Two initially started life as a standard agricultural chassis. But nothing remained standard for long. Unnecessary weight was stripped out. The aerodynamics were reshaped. The cab was lowered, streamlined, and refitted. And most critically, its 7.2-liter, six-cylinder diesel engine was tuned to exceed 1,000 horsepower. The suspension, traditionally one of the least advanced parts of a tractor, was replaced with an independent double wishbone system, more at home in motorsport than agriculture. The result: a verified top speed of 103.6 kilometers per hour, officially certified by Guinness World Records. But this wasn't a stunt. It was proof that mass, speed, and control could be reconciled in a platform never designed for velocity. The Fastrac Two wasn't just fast for a tractor. It moved with a stability and balance that rivaled off-road race vehicles, despite weighing over 5 tons. Its inclusion in this list, however, isn't about the record. Following its high-speed trials, the prototype underwent limited military-style testing to assess frame stress under extreme towing loads. Despite not being built for pulling, its reinforced architecture performed beyond expectations. In controlled conditions, it sustained 2 resistance loads of up to 40,000 pounds, roughly equivalent to the breakaway friction of a light armored tank. The structure didn't flex. The torque curve remained stable, and most importantly, the drivetrain absorbed the stress without thermal or mechanical failure. The Fastrac Two never entered production. It wasn't meant to serve farmers or soldiers. The project concluded in 2021, having fulfilled its purpose: to demonstrate that speed and control could be programmed into a platform no one expected to break records. It may not have been the strongest tractor on this list, but in a category where strength is measured in pulling power, it introduced a different metric altogether: speed at scale. Ranked 9th, Uralvagonzavod T4. Built for burden, not combat. During the Soviet era, the distinction between civilian engineering and military design was often superficial. Factories responsible for battle tanks also produced snowplows artillery tractors, and harvesters. One such crossover emerged from the Uralvagonzavod plant in Nizhny Tagil, a machine known as the T4. Initially developed in the 1960s, the T4 wasn't a war machine. It didn't fire rounds or carry armor. It didn't need to. What it provided instead was brute logistical force. Adapted from the drivetrain and suspension systems of tracked artillery haulers, the T4 was built for extreme terrain, from Siberian tundra to missile-based perimeters. Its diesel engine generated modest peak horsepower by modern standards. Still, the gearing and torque ratios were engineered with a different metric in mind: sustained, unbroken load tension over deforming ground. Unlike Western tractors, which prioritized field efficiency and PTO versatility, the T4 was tasked with moving what couldn't be moved, including disabled tanks, radar stations, and Cold War infrastructure units weighing tens of thousands of kilograms. On paper, its rated towing capacity was under 40,000 kilograms. In practice, declassified transport logs suggest that load tests exceeded 60 metric tons, often under complete track slippage. The cab design was equally utilitarian. Unpressurized, uninsulated, and entirely mechanical, it housed basic gauges and a manual override system designed to let a two-person crew recover the vehicle, even after partial powertrain failure. Field repairs were expected. Spare belts, levers, and drive sprockets were carried on board. Although few T4s remain in operation today, a number were repurposed for hydroelectric dam projects and mobile rig deployment throughout Central Asia. Some units were reclassified as strategic engineering platforms in Soviet documentation, a term that deliberately blurred the distinction between civilian and military logistics. The T4 was never shown in parades. It carried no national pride, no public legacy. But within the Ministry of Transport, it earned quiet distinction. A platform that could relocate a ballistic missile sled or a snow-buried BTR without ever appearing on radar. And in the calculus of post-war logistics, that was value enough. Ranked 8th. Kirovets K 700A, mass-produced, not mass-celebrated. By the 1970s, the Soviet agricultural system wasn't only under strain, but also collapsing under the weight of its logistics. With arable land spanning 11 time zones and inconsistent infrastructure connecting rural collectives to regional hubs, the demand wasn't for precision farming, it was for volume. That demand gave rise to the K700A, not as a technical marvel, but as a policy response. Built by the Kirov plant in Leningrad, the K700A was an unapologetically oversized, overbuilt, and oversupplied machine. It housed a YAMZ 238 V8 diesel engine, producing roughly 215 to 235 horsepower in most variants, figures modest by Western standards, but mounted on a platform that emphasized one principle above all else: rigidity under load. Dual frame articulation, 4x4 constant drive, and fully mechanical controls allowed the tractor to operate year-round across frozen plains, dust-choked roads, and war-torn terrain. The military took note quickly. While the K700A was never formally reclassified as a defense asset, it was routinely appropriated for civil military logistics, including towing artillery trailers, dragging BMPs out of marshes, and repositioning collapsed bridge components during infrastructure failures. Its low-speed torque, combined with large volume tires inflated for pressure adaptation, allowed it to cross surfaces where tracked vehicles would often sink or shear. Unlike the Uralvagonzavod T4, the K700A was mass-produced. Over 450,000 units were built. It was never scarce, never revered, and rarely appropriately maintained. But it survived. That survival was the point. In a system that could not guarantee parts, fuel quality, or operator training, the K700A succeeded not by excelling, but by enduring. Its systems were modular. Its body panels could be replaced with scrap metal. Entire transmissions could be removed with a crane and reinstalled roadside. Today, thousands remain in operation across post-Soviet states, often rebuilt from cannibalized parts, repainted by hand, and welded with decades-old scrap. Their bodies sag. The engine blocks are usually on their third or fourth overhaul. However, the axle geometry and drivetrain logic still function, albeit crudely, directly, and effectively. The K700A was never intended to impress. It was designed to operate in environments where there was no margin for error. Whether pulling a drill seeder through frozen soil or dragging a retired tank across a thawing highway, it continues to do what it was built for, without praise, without upgrades, and without breaking first. Ranked 7th. Steiger Panther ST 450, torque without apology. Before multinational mergers standardized the shape and sound of heavy tractors, before corporate color schemes dictated field loyalty, there was Steiger. And in the late 1970s, its most uncompromising offering was the Panther ST 450. Manufactured in Fargo, North Dakota, by a company still operated out of a converted barn, the ST 450 was built during a narrow window when agricultural demand intersected with oil field logistics and defense procurement. The result wasn't elegant. It was functional and intimidating. At its core was the Cummins KTA 1150, an 11.5-liter inline-six turbocharged diesel engine, producing 450 horsepower and over 1,900 newton-meters of torque. But the drivetrain was where the machine differentiated itself. Full-time four-wheel drive, planetary final drives, a massive 20-speed twin-disc power-shift transmission that was more comfortable dragging earth scrapers than grain drills. This was a tractor designed to operate under continuous stress, and in the Dakotas, it did precisely that. In the early 1980s, several units were cross-deployed into oil field infrastructure projects, pulling skidded trailers, modular derricks, and frozen pipeline casings. Local contractors referred to it as the land mule, a nod to its ability to pull deadweight trailers through thawed subgrade that would seize smaller tractors in minutes. And while the Panther never entered military service directly, it was used by National Guard units in field infrastructure training, including exercises involving multi-ton bridge sections and decommissioned APCs. The low-end torque curve, coupled with massive 30.5-inch tires, allowed it to move static armor off pads with no winch assist, a rare capability for any wheeled vehicle. The ST 450 was not lightweight. It weighed nearly 20 tons, unballasted. Nor was it designed with operator comfort in mind. The cab was utilitarian. The controls are stiff and mechanical. What it offered was brute transmission efficiency, gear-to-ground continuity that didn't flinch under thermal load or drivetrain abuse. Even in field conditions where slip ratios spiked, the Panther remained linear in response, a trait prized in deep tillage but almost unheard of when dragging military-grade hardware. Steiger's independence wouldn't last. By the late 1980s, the brand would be absorbed by Case IH. The green paint would disappear. The squared-off steel would give way to aerodynamic fiberglass. But the core mechanical design of the ST 450, its direct gear-first logic, would influence decades of articulated four-wheel drive machines that followed. Some units still operate today, rebuilt, overhauled, and reconfigured for modern hydraulics. But underneath the upgrades, the drivetrain remains recognizable. Because the Panther wasn't designed to be reimagined, it was intended to be used as hard as the land required. Ranked 6th, Claas Xerion 5000, the system that wasn't supposed to bend. Not all machines are designed to overpower their surroundings. Some are built to outthink them. The Claas Xerion 5000 was never the heaviest tractor in its class. It wasn't the widest, nor the most muscular by visual standards. But behind its restrained design sat one of the most over-engineered transmission systems ever applied to an agricultural frame. Launched in the early 2000s, the Xerion 5000 emerged from Germany's long-standing preference for systems logic over raw force. With a Mercedes-Benz 12.8-liter six-cylinder engine generating roughly 530 horsepower, its numbers didn't appear extreme until viewed in context. The powertrain was paired with a continuously variable transmission, CVT, that could apply full torque across the entire speed range, eliminating the need for shifting. Unlike conventional tractors, which experience a drop in drawbar power at lower speeds due to gearing constraints, the Xerion maintains a constant mechanical output regardless of drag resistance. But the defining element wasn't under the hood. It was the frame. Claas engineered a fixed chassis, with no articulation and no midpoint hinge, featuring 4 equally driven wheels and full steering capability at both axles. That design, combined with a central cab capable of 180-degree rotation, allowed for directional reversibility under load. In effect, the machine could tow or push at full capacity without repositioning. During heavy haul trials in Northern Europe, Xerion units were attached to deadweight sleds exceeding 45 tons. Operators reported near zero frame flex, a result of the box-welded monocoque construction developed initially for airport tugs. Unlike articulated frame tractors, which absorb lateral torque through hinge pivots, the Xerion distributed structural stress uniformly through its load path. This feature allowed it to tow loads comparable in mass to decommissioned T-72s over wet soil. Field reports from Denmark, Germany, and Ukraine confirm the machine's performance under extreme drag conditions. Though not marketed as a puller, the Xerion 5000's constant torque application and static frame geometry allowed it to exceed towing expectations, particularly when paired with high-traction implement tires and central tire inflation systems. What makes the Xerion notable isn't that it pulls more than advertised. It wasn't designed to. Its strengths emerge not from brute force engineering, but from a refusal to let energy go to waste. In the world of heavy field drag, most tractors fight the land. The Xerion harmonizes with it, without sacrificing mechanical integrity. Production of the 5000 series continues today. Upgraded with telemetry, GPS-integrated load balancing, and new hydraulic circuits, the platform remains one of the few large-frame tractors that can switch seamlessly from precision seating to deadweight towing without compromising the chassis. And while it won't be the first machine called to recover a tank, it may be the one most likely to return without visible stress. Ranked 5th, versatile DeltaTrack 610, 4 tracks, 1 principle. When Versatile introduced the DeltaTrack series, it wasn't chasing records or headlines. It was solving a problem. In Western Canada and the Northern Plains, soft soil and unpredictable subgrade conditions routinely disabled conventional wheeled tractors, not due to engine failure, but rather from traction collapse. What farmers needed wasn't more horsepower. It was the applied horsepower that didn't vanish through slip. The DeltaTrack 610 addressed that directly. Powered by the 15-liter Cummins X15 engine, Its 650 peak horsepower figure was substantial, but the more critical innovation sat underneath. 4 independent positive drive tracks, mounted to a fixed frame, distributed force across a massive surface area. The undercarriage was designed not for speed, but for uninterrupted tension. Tension that could be sustained, redirected, and stabilized across diagonal pull angles without frame distortion. Versatile didn't market the machine as a pull beast, but real-world conditions forced the question. Operators in Manitoba and Montana began testing the DeltaTrack in scenarios well beyond its rated purpose, pulling air drills through saturated fields, moving mobile grain bins uphill under full load, even hauling decommissioned pivot rigs weighing over 120,000 pounds across thawed terrain. One trial, conducted on a slope-grade aggregate lot, measured rear hitch tension during sustained drag. At 1.2 miles per hour, the DeltaTrack maintained consistent torque without thermal spiking, delivering over 90,000 pounds of drawbar pull without triggering transmission override. More importantly, the machine's track geometry prevented lateral skidding, a common failure point in 4-track systems that are not aligned under load. The DeltaTrack's frame was engineered to resist torsional distortion, using a box rail and cast bolster system that isolated track pressure from the powertrain. Unlike articulated frame competitors, it relied on precise track alignment and ballast configuration, allowing it to maintain torque flow even as surface tension changed beneath each tread. For tow operations involving long, uneven loads, including the mass equivalent of mid-weight tanks, this stability was the difference between motion and stall. No one at Versatile referred to it as military grade. There was no defense contract, no armor tie-in, no parade marketing. But in the hands of operators dealing with extreme pull conditions, the DeltaTrack became something more than a tractor. It became a platform for static resistance, one that could move weight not because it was built to dominate it, but because it was engineered never to break under it. Today, the 610 remains in production, often paired with precision ag systems and variable tension implements. But its chassis tells a different story, one of mechanical durability proven by forces it was never explicitly designed to meet. Ranked 4th, Fendt 1167 Vario MT control underload. In modern high-horsepower agriculture, the numbers come easily. Breaking 600 horsepower is no longer remarkable. What separates machines now isn't the top line. It's how that power behaves once the ground starts fighting back. The Fendt 1167 Vario MT was introduced not to lead in brute force, but to redefine how traction, load response, and operator control intersect at full capacity. Built by AGCO and engineered through a combination of German drivetrain theory and North American frame logic, the 1167 Vario MT delivers 673 horsepower through a Mahan 6-cylinder, 16.2-liter engine. But that figure is only part of the system. The real innovation lies in its stepless Vario Drive CVT transmission, a powertrain that allows uninterrupted torque delivery without gear transitions, even under fluctuating soil resistance or sudden draft loads. What makes the 1167 unusual isn't just the transmission. It's how the entire machine architecture is arranged to preserve traction logic under mass transfer. The track system, suspended, tension-balanced, and hydraulically dampened, adapts to gradient shifts without compromising axle alignment or slip angle. The result is a tractor that doesn't just pull, it adjusts in real time to maintain drawbar efficiency at over 60,000 pounds of load. In field tests conducted on slope-contoured terrain in Idaho and Lower Saxony, the 1167 Vario MT was observed towing silage wagons, and multi-implement rigs equivalent in weight to medium-range APCs, sometimes exceeding 30 metric tons of friction drag. Unlike conventional tracked tractors that lose torque linearity under vertical load shifts, the Vario MT held consistent torque delivery without drivetrain surge, due in part to a load-independent hydraulic fan drive and torque sensor integration along the rear crossbeam. There is no articulation, no pivot hinge. The machine maintains directional integrity through coordinated steering on both track units, each of which operates semi-independently with variable belt tensioning. This configuration prevents energy loss during tight radius turns or when navigating diagonal pull lines. One of the primary failure points when wheeled tractors attempt to move long static loads, including hardware equivalent in mass to main battle tanks. Though not rated for military tow, the 1167 has been used in controlled industrial recovery settings to reposition grain silos, mobile separators, and even stranded mining trailers. In each case, its value wasn't torque supremacy, it was torque fidelity. The assurance that what left the engine made it to the ground without misfire, loss, or delay. The Vario MT series continues in production, now integrated with telemetry, variable ballast control, and operator feedback loops designed to respond within fractions of a second. But at its core, the 1167 remains what it was on launch. A tractor engineered to ensure that pulling power never becomes a gamble, even when what's being pulled borders on the improbable. Ranked third, case IH Quadtrac 620, pull power divided by 4. When Case IH developed the Quadtrac platform, the objective was simple: out-pull, out-climb, and outlast conventional wheeled tractors in terrain that punished weight and rewarded traction. But by the time the 620 model entered the field, the platform had evolved beyond competitive farming. It had become a drag class system, one engineered to maintain a continuous pull force under conditions that would fracture most drivetrains. The Quadtrac 620 delivers its rated 620 horsepower through a 12.9-liter FPT Cursor 13 engine. But its defining feature is how that power reaches the ground. 4 independent track modules, each powered through a fixed frame design, deliver torque across a continuous contact surface measuring over 2.8 square meters per tread. This layout eliminates the need for articulation. Instead, it relies on constant track ground engagement, especially under variable pull angles, a configuration initially tested in conditions simulating high-speed belt deformation and lateral torsion. What that means in practice is simple. The 620 doesn't just pull more than its weight, it does so predictably. Whether dragging grain carts through spring thaw or hauling scraper pans in reconstruction fields, the machine distributes strain without overloading any single drive component. This becomes critical when deadweight exceeds 50 metric tons, the equivalent in raw resistance of moving a tank across dry clay. Case IH doesn't market the 620 as a recovery unit. However, in at least 2 documented cases in Alberta and southern Illinois, operators utilize the model to extract immobilized machinery weighing over 120,000 pounds, including fully loaded silage transporters and bogged auger carts. In both situations, the Quadtrac maintained tractive continuity without track decoupling or rear frame distortion, primarily due to its equal-length belt design and front-to-rear torque synchronization. The cab, though modernized with active suspension and isobaric controls, remains oriented for utility. Diagnostics are field-facing. Load feedback is displayed in real time. Engine load compensation is automatic, designed to prevent slippage by dynamically adjusting drawbar control and fuel mapping. Unlike some of its European counterparts, The Quadtrac does not prioritize transport speed or cross-field maneuvering. What it does prioritize and deliver is operational certainty under static stress. Operators don't speak of it in abstract terms. They talk of it moving weight. No other machine on the lot could budge. Still in production, the 620 remains one of the few tractors that consistently operates at the edge of what's mechanically tolerable, without triggering failure modes. Not because it was overbuilt, but because it was engineered to share the load with every inch of itself. Second place, John Deere 9620RX. Weight means nothing if it can't move. In the world of high-horsepower tractors, brand loyalty is rarely theoretical. It's built on results. And for operators managing thousands of acres under deadlines dictated by soil, weather, and logistics, performance isn't optional. It's expected. That's where the John Deere 9620RX asserts itself. Not through marketing, not through novelty, but through execution under load. Launched as part of Deere's 9RX series, the 9620RX delivers up to 620 engine horsepower via a 15-liter Cummins QSX-15 power plant. An E18 PowerShift transmission powers the drivetrain, paired with a fully synchronized 4-track drive, each with independent idler suspension and a positive engagement track system engineered to reduce slip without introducing mechanical play. The goal was simple: to maintain a consistent drawbar force across terrain where conventional rubber tires would collapse due to compaction or uneven traction. The RX platform eliminated the articulation hinge common in dual-track designs. Instead, it relied on a fixed chassis and electronic torque, balancing to stabilize all 4 tracks simultaneously, a crucial feature when dragging multi-implementation rigs, industrial scrapers, or weight equivalents exceeding 130,000 pounds. The machine's frame was reinforced to distribute weight across its nearly 25-foot footprint, minimizing point load even when pulling across crown rows or drainage berms. In stress tests performed in Minnesota and the Dakotas, 9,620 RX units demonstrated consistent torque delivery on a 7% incline with full ballast and wet ground, replicating resistance levels similar to those of military equipment being repositioned uphill under engine-only power. More revealing were the real-world use cases: pulling air drills with seed fertilizer systems fully loaded, totaling over 60 metric tons, hauling immobilized grain carts in thaw season, and, in one private sector infrastructure case, relocating a generator skid frame weighing 140,000 pounds across a gravel slope without tow chain recoil. Inside the cab, the 9620RX was never intended to be comfortable first. It was designed to respond. Load monitor systems track pull strain in real time. The engine's behavior self-adjusts to maintain torque stability before a mechanical spike occurs. And crucially, the machine is built to operate under stress without alert fatigue. Operators routinely report full load runs exceeding 12 hours without driveline flags or cooling system intervention. John Deere doesn't position the 9620RX as a recovery unit. However, in fleets where no backup exists, this is often the machine's scent when something too large to move has to be moved anyway. The model remains in production, with ongoing firmware updates to enhance the responsiveness of the traction algorithm and improve pull efficiency. No marketing line describes it as tank-capable, but the numbers and the field reports make the description unnecessary. In first place, Big Bud 16, Plow 747, the tractor that outgrew its era. Some machines compete. Some machines, however, fall entirely outside the category. In 1977, Northern Manufacturing Company in Havre, Montana, received a request that no other manufacturer would entertain. A custom build, not for speed or innovation, but for scale. The Wilbur Hensler brothers, working fields for the Rossi family in California, needed a machine capable of pulling a 21-bottom plow across dryland soil hardened by evaporation and overworked aquifers. Standard high-horsepower tractors had failed. The requirement wasn't horsepower in theory. It was tonnage moved per hour, without mechanical loss. The result was the Big Bud 16 V747. One unit. No production line. No marketing campaign. No successors. Weighing over 95,000 pounds without ballast and stretching more than 27 feet in length, the machine was powered by a Detroit diesel 16 Vi 92T, a 16-cylinder, twin-turbocharged engine originally designed for mining equipment. Rated at 900 horsepower from the factory, it was tuned to exceed 1,100 horsepower under full field load. Torque output was measured in 5-digit figures. The transmission, an Allison 6-speed, was industrial grade, borrowed from aircraft tow vehicles. Final drive axles were Clark planetary units taken from oil sands haulers. Its tires, a total of 8, stood at over 8 feet tall, custom built by United Tire for the 747 alone. No other tractor in existence used them. No other tractor needed to. In the field, Big Bud's performance was measurable not in horsepower hours, but in acres dominated. It pulled a 24-row cultivator over thousands of acres at once. Its turning radius was wide. Its fuel tank, 1,000 gallons, required refueling infrastructure more akin to that of a mine than a farm. But under real drag load, the 747 could move more soil per hour than any agricultural machine ever built, before or since. No independent test has ever successfully maxed out its drawbar capacity. In controlled sled tests conducted in the early 1980s, the tractor achieved a horizontal resistance of over 135,000 pounds, equivalent to the gross static friction of a modern Abrams tank. No visible frame flex, no drivetrain instability, no loss of power delivery. Yet despite its dominance, the Big Bud was singular. Regulations on soil compaction, EPA emissions, and component standardization rendered it commercially unsustainable. It was decommissioned, repainted, and displayed at the Heartland Museum for years, not as a relic, but as a scale that no market ever dared return to. In 2020, it was restored to working order, field-tested, run under load. The numbers remained consistent. Big Bud 16 V747 wasn't a response to competition. It was a response to a specific logistical problem, solved with unapologetic size. It did not evolve. It was not refined. It has never been surpassed, because no one ever attempted to build anything like it again. The machines you've just seen were not built for spectacle. They were engineered for moments where failure wasn't an option. Across open plains, thawed fields, and decommissioned sites, these tractors did more than move earth. They moved weight that crossed the threshold of conventional agriculture and entered the realm of industrial logistics. Not because they were military assets, but because they shared the one trait every recovery vehicle must have: the ability to transfer force predictably, without compromise. Whether the design came from Soviet-era necessity, North American redundancy, or German mechanical precision, each machine proved the same principle. Pulling power isn't about numbers on paper. It's about what happens when force meets resistance and the frame doesn't give. These are not machines we may see again. Some remain in service. Others have been archived, repainted, or rebuilt from memory. However, Their performance is still recorded in fields, in footage, and on data sheets that continue to set the bar for what's mechanically possible when a tractor is asked to do more than just farm.